All right, hi everyone. So this lecture video is going to be over chapter 6, sections 6.1 to 6.5. We're going to be doing nomenclature, which means you guys get to learn how to name compounds. Now there are 4 types of compounds that you guys are going to learn how to name. So go ahead and get out a piece of paper. This is how I would take notes. And then if you have this piece of paper in front of you, it's going to be like really easy to, do the quizzes and exams, right? Because it will have all the naming rules of these 4 classes of compounds that we're going to learn how to name. So get out a piece of paper. You are going to divide it into 4 quadrants like that. And so that's going to represent each classification of compounds that we're going to learn how to name. So the first one is ionic compounds. Okay, that'll be your first quadrant. Okay, and then the next one, you can label covalent compound naming. Okay. Then we go to the binary acids naming. And finally, the oxoacid naming. Okay. So that's gonna be your piece of paper, right? And now since I don't have room, I'm gonna go through each one of these quadrants at a time on the board. Okay, so the first quadrant, we're gonna name ionic compounds. And first, right, we have to know how to spot ionic compounds, otherwise we won't be able to name it, right? So you guys already know that ionic compound is between a metal and non-metal, right? So you can spot that and you'd be like, okay, I'm going to use my ionic naming rules. But more generally, it is between a cation and an anion, okay? So not always is an ionic compound between metal and non-metal. It's just simply between a cation and an anion. So something like ammonium nitrate or ammonium chloride, ammonium is actually a non-metal. So let's get into the rules. So the first is when you see the compound, the first element will get the metal name because the metal will always be written first. Okay. Let's say first element gets element name. And then the second element, the nonmetal, if it is monatomic, then you will drop the element ending. You keep just the roots of the element, and then you add the IDE ending, IDE. Okay. If it is a polyatomic, then it just gets the polyatomic name. Okay. One more rule. If the metal is a variable charge metal, you're going to use Roman numerals in parentheses to denote the charge of the metal. Okay. So let's talk about the variable charge metal first. Almost all metals are variable charge. There's a few exceptions. So it's easier to memorize the fixed charge metal list. Okay, so fixed charge metal. Look at your periodic table, everybody. It's group 1A, so the first column of your periodic table, and group 2A, the second column of your periodic table. And then these ones, aluminum, 3+, zinc 2+, cadmium 2+, and silver plus. Okay, so it's a very short list of metals that are fixed charge. If your metals do not fall into this list, then it's considered a variable charge metal, and therefore you'll have to use Roman numeral. Okay, let's practice our Roman numerals too, just in case you guys have forgotten. So for 1, we just do I, right? So if you see I, that means the metal has a charge of 1+. If you see I, then the metal has a charge of 2+. I is 3+. IV is 4+. V is 5+. VI is 6+. VII is 7+. And then VIII would be 8+. Okay, so we don't go past that. You're not going to see charge that high. Okay, but just so that you guys remember, right? So now let's do some examples so you guys see how these work. All right, so one of the examples you guys have heard over and over again is sodium chloride, right? Well, sodium chloride is an ionic compound, right? Because it's NaCl. Right, Na is a metal and Cl is a non-metal. So first, identify what it is before you start naming it. All right, I know it's ionic, so I'm going to use this rule. So this first element gets the element name. So Na, first element, it's going to get a name, sodium. All right, okay. And it says the non-metal. So the non-metal following. If it's monatomic, meaning it's just a single atom, which this one is, right? It's just a single atom. Then it gets root plus IDE. Okay, so instead of saying chlorine, we're gonna just say the root of chlorine, which is chlor, right? And then we're gonna change the ending to IDE. It's always ide. Okay, and I think we have talked about this in a previous videos as well, how to name monatomic ions, right? It's always root plus IDE. So sodium, chlor, be your root, right? And I. Okay, so that's how it works. There's the root, and there's the ending. Okay. Let's try another one. Let's do SR, Br2. Okay. Now, when you first look at that, you gotta say, oh, okay, I know it's an ionic compound. Why? Because I have a metal, and Br is the non-metal. Okay. So the first element's gonna get the element name. That's strontium. Okay. And Br is bromine, right? You're gonna keep the root, which is bro, and then you have the IDE ending, which is bro, makes it bromide, right? So again, bromine turns into bromide, right? Root plus IDE, okay? And how do you know, right? Again, how do you know that you need the IDE ending? Because it's monatomic. I mean, even though there are 2 bromines here, but it's the same type, right? It's just one type of atom. So it gets bromide. Okay. Let's do another one. FeCl2. Okay. So now I have first element is iron, right? Fe. And then again, I have monatomic. So I know that it's, going to be chloride. But notice that iron is not a fixed charge metal. Okay. In our previous 2 examples, sodium is in group 1A, right? And strontium is in group 2A. Go ahead and verify that for yourself. So both sodium and strontium belong to fixed charge metal, which means you don't need Roman numeral in order to denote their charge. Why is that? Because group 1A metals is always 1 plus, group 2A metals is always 2 plus. There's no ambiguity, right? However, for iron, there are multiple charges that iron can be. So that's why iron is considered a variable charge metal, and therefore you will need to use Roman numeral to denote the charge of the metal. All right, so I know that I'm going to need Roman numeral, but what's going to go inside? Well, I can use the nonmetal to figure out the charge of the metal. When ionic compounds come together, their total charge must be 0. Okay, so in sodium chloride, for example, the sodium is positively charged, right? Because it's in group 1A, and the Cl is negatively charged, right? Because it's in group 7A, right? So a plus and a minus will come together, and it makes a neutral sodium chloride compound, right? In SRBr2, right? Your strontium is in group 2A, so it'll be 2 plus. And bromine is in group 7A, so it's negative. But you have 2 of them, right? You have 2 bromines. So it's 2 negative, balancing out a 2 plus charge, right? And therefore making the whole thing neutral. Okay, so that's very key. Is in that ionic compounds, the compounds have to be neutral, right? So there it is. Okay, so even though one is a plus and one is some plus, one is some minus, right? They have to come together to be neutral overall. Okay, so that's how you're going to be able to tell what charge iron is, because chlorine is in group 7A. So chlorine is going to have a negative charge on it, right? However, there are 2 chlorines, so that's 2 minus, right? You have a 2 minus, well, iron then has to be 2 plus to balance out that 2 minus, okay? So you see how I make little notes? You can do that as well, just to keep track of the charges, okay? But once you figure that out, now you're going to put in iron 2, because you know that iron is 2 plus. Iron 2, then chloride, okay? So notice how it's written differently than these, right? These didn't need Roman numerals, right? Because they're fixed charge. Okay. Let's do another one. We can say FeCl3. FeCl3, again, is going to be iron, okay? But now you can see that that's a different charge, right? Because now we have 3 chlorines instead of 2. So if each chlorine is negative, each chloride is negative, then we have 3 total. That's 3 minus total, and therefore the iron is going to be 3 plus, right, to neutralize it out. So you put in parentheses, iron 3, chloride. Okay, now you can really see why this is important, why the Roman numeral is important. Because let's say you're in the lab and I ask you, bring me some iron chloride. You should be like really confused, because you're gonna be like, well, which one do you want, right? Do you want the iron 2 chloride, or do you want the iron 3 chloride, right? Because both are iron chlorides, however, they're not the same thing. An iron 2 chloride behaves very differently than an iron 3 chloride, right? And so that's why you have to make that distinction for all of these metals that are variable charge. And I'll give you guys a hint, right? You can see where the fixed charge metals are first 2 columns, and then a select few here that you should memorize. But most of your variable charge metals is gonna be in the middle where the transition metals are, right? So transition metals are going to be variable charge, and iron's there. So you're always going to need Roman numeral. Okay. Let's do another one here. Na2SO4. Okay. Now, first of all, how do we know that Na2SO4 is ionic? Well, Na is a metal, right? And SO4 is a collection of nonmetals. So you have metal, nonmetal. It's just a collection of nonmetals, but you should recognize it as one of your polyatomics called sulfate. Okay. Now, you guys may not be able, not be familiar with your polyatomics yet, but I want you to get familiarized as soon as possible, because it's going to be talked about a lot in the class, and you're going to be using it beyond this class even. So you should know your polyatomics as soon as possible. Memorize it, right? In this class right now, you don't have to, but in Chem 1, if you're going to go on to Chem 1, you're going to have to memorize it. So my suggestion to you is just memorize it. So I'm showing you where it is on Canvas. So it's going to be under week 4 module. You're going to see a document called Polyatomic Ions and Elements to Learn. It's a PDF that's underneath the lecture material. Okay. Go ahead and download it like I did, and then open it. So you're going to see a list of polyatomic ions that you need to learn. Go ahead and learn both list A and list B. Okay. Best way to do this, I find, is flashcards, right? Or an app on your phone that, quiz you like flashcards. So important thing that you have to know, okay, is not just the name of the ion, but also the symbol and the charge. Let me zoom in here. Okay, so you can see, for example, if I say nitrite, then you should know that it's NO2 negative, okay? Now, why is it called polyatomic? Because it's multi-atoms that are charged. So in, like, say, Cl minus, it's only the one chlorine atom that's charged, right? Cl minus, it's chloride. However, here, you have multiple non-metal atoms that are charged. So you have an NO2, and collectively, they carry the negative charge. That's why we call it a polyatomic ion, okay? And they are all mostly anions, as you can see. They're all some negative, right? Some are 2 negative, some are 3 negative. But there's a couple that are cations that you should know. Ammonium, NH4 plus, and then hydronium is H3O plus. Right? So you definitely should know those, know all of these. So start learning them already, okay? As you can see, there are a lot. Another thing I want to point out to you, which is going to be important later, is that all of the polyatomics end in either ITE, ite, or ATE, ate, right? So you have chlorite, chlorate, hypobromite, or bromite, or bromate, right? So all either ite or ate. Okay, so just see that. Okay, let's go back to the board and we'll continue with naming Na2SO4. Okay, so as you can see, SO4, SO4, if you look at SO4, it's 2 minus, and it's called a sulfate. Okay, so it makes sense that SO4 is 2 minus because here we got 2 sodiums, and sodiums are in group 1A. So I know each sodium is a plus, right? And so that's why it needs to be counterbalanced by a sulfate, right? Because you have 2 sodiums here, right? So Na2SO4 is a compound, but NaSO4 would not be one, right? Because it wouldn't be electrically neutral. Okay, so we're just going to name it. First element gets element name, so it'll be sodium. And we check real quick, is sodium a fixed charge or a variable charge metal? Oh, sodium's a fixed charge, so I won't need Roman numerals. And I move on, and it says if it's a polyatomic as your nonmetal, just use the polyatomic name, which we saw was sulfate. So pretty straightforward. Just use the polyatomic name. So we say sodium sulfate. Okay. Okay, let's do some more examples. Okay, this one. So again, how do we know that this is ionic compound? Well, copper is the metal, and you need to start recognizing that NO3 is one of your polyatomics, and that is called nitrate, right? And if you look there, NO3, NO3 minus is nitrate. okay? So NO3 has a charge of 1 minus, okay? And there are 2 nitrates. So notice if there are multiple polyatomics, the polyatomic itself, it should be written in parentheses, and then you use a subscript to denote how many nitrates there are, okay? So it might look a little confusing at first, but just think of how the functions that parentheses serve. It's saying that there are 2 units of what's inside the parentheses. So meaning if I was to write this out, this is what I have, right? And now with copper, we know that it's a variable charge metal because it doesn't belong in the fixed charge. So it needs to have a Roman numeral to denote its charge. Well, this is where this comes in handy. Use your non-metal to figure out your metal's charge. That's how it always works. So that each nitrate is 1 minus. You got 2 nitrates total, so that's 2 minus. So therefore the copper has to be what charge, everybody? 2 plus, right? So kind of like break it down like this, it's easier to see, right? And so that's what actually this notation is telling you, okay? Physically, you got 2 nitrates, 2, 1, copper, 2 plus, right? And together, they're electrically neutral. Okay? So that's what this notation is, okay? But of course, we don't write it like that. We write it like this. So you should learn how to read that. So copper, 2 nitrate. And that's it, right? Because the polyatomic just gets the polyatomic name. Okay. All right, let's do a couple examples where we do it the other way around. So I would give the long name and then you give the chemical formula. So what if I say cobalt 2 iodide, for example? Okay, so you got some clues here to figure out what the chemical formula is. That the thing in parentheses gives you a big clue already, because remember that tells you the charge. So when I see that 2, I think 2 plus and write it on top of the cobalt. So I know the cobalt is 2 plus. Now iodide, I recognize that as something, iodine, right? Iodine, but charge. So where is iodine on the periodic table? It's in group 7A, right? And so it's going to have a charge of 1 minus, right? And once again, 1 electron to get to the noble gas. So iodine is 1 minus. Okay, figure that out first. Figure out the charges first. Now put it together to make it neutral. Okay, so I need 2 iodides, right, to make it 2 minus to cancel out the 2 plus. So my cobalt, the symbol for that is CO, and this is why you gotta know your symbols, right? CO. Now iodide is I, but I need 2 of them, right, to balance out and make it neutral, because iodide's only 1 minus. Okay, so there it is, COI2. Okay, so you want to know, know it both way, right? Going from chemical formula to long name back to chemical formula. All right, let's do some more. How about this one? Calcium nitride. Calcium nitride. Okay, well, remember, do the charges first. Calcium is 2 plus. Nitride, see, it's an IDE ending, so it's going to be a charge. It's going to be a monatomic charge, right? So look at where nitrogen is on the periodic table. It's in group 5A. Quickest way to the noble gas is 3 to the right, which means it wants to gain 3 electrons. And so, therefore, nitride is 3 minus. Okay. So now think about how many calciums you need and how many nitrides you need in order for the number to go down to 0, right? If you just do calcium, 1 calcium and 1 nitride, you see that the charges is not going to cancel out, right? 2 plus and 3 minus don't cancel out. So think about, the trick is to think about the lowest common denominator between 2 and 3, okay? That's going to be 6, right? Everybody agrees? 6. And so now take 6 and divide by each of the charge, and you'll get the number of each atom you need, okay? So 6, the lowest common denominator, divide by 2 is 3. So I'll need 3 calciums. 6 divided by 3 is 2. So I'll need 2 N's, okay? So Ca3N2, okay? If you want to check your answer, just put a 2 plus on top of calcium, put a 3 minus on top of nitrogen, and 2 plus times 3 is 6 plus, 3 minus times 2 is 6 minus. You see 6 plus and 6 minus adds up to 0, right? Remember, neutral overall, right? You want your compounds neutral overall. Okay, let's do another one. Okay, let's do zinc bromate. All right, so zinc, okay, that's fixed charge metal. You guys remember? Zinc is a fixed charge metal. Okay. So you're not gonna have the parentheses to tell you what charge it is. Okay. See, in cobalt you did, but they're not gonna write that for zinc because you're supposed to know that. You're supposed to know that zinc is 2 plus. Okay, that's why you want to memorize that. Okay. So zinc is 2 plus. Bromate. Let's go ahead and we can look on here for now that we don't know it as well. Okay, bromate is BrO3 minus. BrO3 minus. We know that it's negatively charged. Okay. So Zn, okay, zinc is 2 plus. We will need 2 bromates, won't we? Because that's a negative charge, and we need to bounce out 2 positive. So we'll need 2 bromates. Remember, bromate is BrO3. But since we need 2 of them, I'm going to put bromate in parentheses and put a little subscript 2 to denote that there are 2 of them. Okay, so that's how you write zinc bromate. Okay. All right, guys. So as I always say, I can do a bazillion examples. I've probably done a dozen of them now. But it's not going to help you until you go and practice on your own. Okay, so you have the list of rules here, pretty straightforward rules. Follow them and just make sure that you can do this pretty quick. Okay, we're going to move on to the next quadrant. We're going to name covalent compounds. Okay, so first we got to know how to spot covalent compounds. It's pretty easy. It's going to be non-metal and non-metal. Okay? Okay, so unlike ionic, which is metal, non-metal, covalent, non-metal, non-metal. Okay. So let's go straight to the rules. The first element gets the element name. The second element gets roots plus IDE. Very similar to in ionic for the non-metal, for the monatomic, okay? Exactly like that. Just use root and IDE, okay? But there's one more catch. You have to use prefixes to denote how many atoms there are. Okay. And the exception is don't use mono for the first element. Okay. Don't worry, these rules are going to make a lot more sense when we go through the examples. But let's talk about the prefixes here, right? let's review. Let's do it the other way around. Okay, so the prefix is going to tell you how many. If you just have one, that's mono. Okay, two is di. You guys probably know some of these already, so which makes it good. If you already know some of it, makes the learning easier. All right, three is tri, right? Four, guess what? Tetra. And I'll explain in a second too why I put these vowels in parentheses. Five, penta. Six, hexa. Seven, hepta. Eight, octa. Nine, nona. And 10, deca. Well, I don't know if you guys can see that. Let me rewrite. Dec. D-E-C-A, right? Deca. Okay, so one more time. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay. All right, let's dive right into some examples. And 205, for example. Okay, first of all, how do you know that it's gonna get the covalent naming rules? Well, it's a covalent compound because it's non-metal and non-metal, right? Nitrogen's a non-metal, oxygen's a non-metal. Okay, so you're gonna use these rules. It says first element gets element name, so that's gonna be nitrogen, but there are two of them, so you're gonna do right dinitrogen. Okay, see how the prefix comes into play, dinitrogen. And then a 5, the prefix 5 is penta. Okay, and then it says the second element gets root and IDE. It's oxygen, just take the root, ox, add IDE, oxide, right? But there are 5 of them, so you're gonna do penta oxide. Okay, that sounds a little like too much of a mouthful, like pentaoxide, right? And so we just shorten it to be pentoxide. And that's why these vowels at the end are in parentheses. You don't use them if the next letter is also a vowel. You can leave it out. So instead of saying pentaoxide, you can just say pentoxide, right? It's smoother, okay? All right, let's do CO2. No, everybody knows this one, right? Carbon dioxide, right? That's why, right? So it's like you already knew some of these, but now you really know the rules. You can name anything, right? So that's di because of the 2, oxide, carbon. Now notice, carbon, we don't use mono for the first element. That's why it's not monocarbon dioxide. It's just carbon dioxide because we don't use mono for the first element, okay? So keep that in mind. As opposed to CO, here you see the use of mono, so it's carbon monoxide, okay? Right? Because we do use the mono for the second element. And notice too, we drop the O so that it's not monoxide, right? Double O. So you can drop the vowel again because the following letter is a vowel. Let's try this one. P4S10. Okay. 4 is tetra. P is phosphorus, right? So tetra, phosphorus. And then 10 is dec, right? Deca. And then S is sulfur. Keep the root, sulf, and add I, sulfide. So deca, sulfide. Pretty straightforward, right? Yep, that's all there is to it. So we're not going to keep going. Quite easy. You know, practice some more, but that's really all there is to it. There's not much more, right? The ionic compound naming, it was a lot more involved. This one, fortunately, it's a lot easier. Okay, so we don't have to dwell on it anymore. Just move on to the next quadrant, everyone. Is acid naming. But first, just a small lesson on acids before we go into naming acids. What is acid? Okay. Well, you guys have heard of acid, probably in the context that it's probably not something you want to bathe in, right? Not something you want to drink or touch. It's very corrosive, and certainly is, right? And the corrosiveness of acid is due to the proton, okay? So let's talk about that first. The way that acids are written in a chemical formula, the way that it's written, you can tell that's an acid because it will lead with H. But this H is not with just any H. This H is actually a proton, okay? So acids will lead with H. And the definition by Arrhenius, who is the grandfather of acid-base chemistry. So the first definition ever for an acid was, Arrhenius that came up with it. And well, let's make it even more concise than that. Anything that produces H plus in water. Okay, so it'll contain a proton and it'll produce H plus in water, which will turn into H3O plus, which is the hydronium ion. Hydronium is H3O positive. Okay, now how does this do this? Well, let me show you. This is a quintessential acid here as an example. Hydrochloric acid. I'm sure you guys have all heard of it. Hydrochloric acid. Notice it leads with H. That's how I know that this thing is an acid, right? It leads with H, which is actually an H plus. You guys know what an H plus is? Well, plus means electrons lost, right? So H plus is hydrogen without its electron, okay? And it's very reactive. It's what makes an acid an acid. It's this H plus that like eats away at everything, right? That's why it's so corrosive. Okay, so if you have HCl and you put it in water, what happens is it's gonna dissociate to become, this is H plus, remember the H, that H is always the proton, and then the Cl is minus, okay? And so that's why it's neutral, right? H plus and a Cl minus, and it's neutral. So this H plus gets, now you guys know Lewis structure, so I just drew water, right? Remember water, the oxygen has two lone pairs. And H plus is deprived of the electron. So of course this oxygen is gonna grab this proton, okay? So water basically just soaks up the proton and it becomes H3O plus, right? So it basically is this now. Okay, the whole thing is positively charged, right? And this is what we call hydronium, which is H3O plus, okay? So in an acid, the H plus and the hydronium is synonymous because all hydronium is just an H plus that's attached to water, right? And so since there's so much water around in these acid solutions, the water is just going to soak up that H plus. And so we can think of an Arrhenius acid that as anything that produces hydronium in water, produces H plus in water, right? One and the same, okay? So it's this ion that makes a solution acidic. And you guys actually have experienced acidity in like your foods. So if you're eating limes or lemons, oranges, any citrus fruits is sour, right? And that sour taste is due to the citric acid. That's why it's called citrus fruits, right? Because of the citric acid, and that's why you have that tartness. That's the hydronium ions that you're tasting in your fruits. Okay. Now citric acid is, a weaker acid, right? So it's okay to eat that. You've also eaten vinegar, which is acetic acid, also a weak acid. These things you can eat and it's okay. But HCl, for example, is not something that you're gonna want to ingest, right? Although it is already in your stomach, right? This is the HCl that digests your food. It's the acid in your stomach. Okay. Let's also talk quickly about the strengths of acid. So what makes an acid strong versus weak? So the one that I just showed you guys, HCl, dissociates in water to become H plus and Cl minus, or we can call it, hydronium, right? We can just actually write a full equation. Okay. So for each HCl, if you have 100 of them, for example, a strong acid will put out 100 ions, 100 hydronium. So if you had 100 HCl, it's going to put out 100% hydronium. Okay, meaning this acid will completely dissociate to give hydroniums 100%. Okay, and that's why it's considered strong. A weak acid, on the other hand, and a weak acid would be like HF. If you put that in water, only 3% will dissociate. Okay, so only 3 out of the 100 HF will give hydronium. So there won't be a lot of hydronium in solution. So that's why it's considered a less acidic than this one, right? It's weaker in acidity than HCl, which deposits 100% of hydronium, right? So what it means is, you're gonna still have 97 of the HF intact, right? Okay. And oftentimes for these weak acids, you will see that it's the arrow is like this, right? Instead of like this. So when the arrow is just to the right, it means you have strong acid. Everything dissociates to form these ions. If you have a double-headed arrow, that means that it's weak, and so only some of it is going to dissociate, and a lot of it is left, undissociated, and so that's why you have an arrow pointing to the left. All right, so that's enough. We're going to have a whole chapter devoted to acids and bases. So we can go into more detail later. But now that you guys know a little bit about acids, remember it leads with H. And let's go to our next quadrant. And we'll do the binary acid naming. Okay. So again, right, how do you spot acids? Leads with H. And what is or H plus, right? And what does binary mean? 2. So a binary acid is an acid that is only 2 types of atoms. Only has 2 types of atoms in it. Okay. And the rule is use prefix hydro followed by the roots followed by ic acid. Super easy. So we just did it. HCl. Okay. How should we name that? Hydro. Okay. The root, the Cl, is chlor, right? Because it's chlorine. It's all attached too. Chlor. Okay. And then ic acid. Okay. All together. Hydrochloric, space, and then acid. There's only a space before the acid. Okay. So hydrochloric acid. Let's try this one, everyone. Hydro. It's a bromine, right? Bromic acid. How about HI? Hydro. It's iodine, but you're not going to say that, right? It's going to be iodic acid. Okay, let's try another one. H2S. Now, in H2S, you can see that there are 3 atoms, but there's only 2 types of atoms, right? Just a hydrogen and a sulfur still. So it's still considered a binary acid, right? These are binary, two types of atoms, 2 types of atoms, right? That's why they're considered binary, okay? So hydro, sulfuric acid, okay? Sulfur sometimes is has a little exception where it keeps the whole name of the element. So it's not hydrosulfic acid, but it keeps the whole name sulfur and then ic acid. For sulfur, it's like that. See what else? HF, one more. Hydrofluoric acid. Right. Fluorine turns into fluorine. All right. That's it. That's all there is to binary acid naming. Let's go to our last quadrant. We're gonna do oxo acid. Okay, again, how do we spot an oxo acid? It contains oxygen. Okay, it's an acid that contains oxygen in it. We know how to spot an acid. Leads with H, right? The chemical formula leads with H, but it has oxygen in it. That's why it's called oxo acid. So these acids are derived from your polyatomic ions. Anions specifically, okay? And remember earlier that I showed you guys the pattern you keep seeing for polyatomic is that it either ends in "ite" or "ate." You see that? "Ite" or "ate" all the way down. "Ite" or "ate." Okay. So this ending you're gonna use to help you name your oxo acids. Okay. So "ate" will turn into ic acid. It's the ending, okay? The ending of the polyatomic. Ite turns into this acid. Okay. So yeah, let's do one. HNO3. So HNO3, you have to notice that NO3 is one of your polyatomic. You have to recognize that, right? Otherwise, you can't name it. So NO3 minus is nitrate. You gotta know that. Because now nitrate, right? This 8 turns into ic acid, right? Right? Very easy. Let's do another one. H2SO4. SO4, as you can see, is 2 negative charge, and it's called sulfate. So SO4 2 negative is called sulfate. That's where it's coming from. Okay. And 8 is going to turn into ic. But remember, sulfur keeps its whole name. So this is sulfuric acid. Okay. Do another one. H3PO4. PO4, you can see here, is 3 negative, and it's phosphate. Okay. So phosphate, right? You want to identify the polyatomic that comes from first, and then change your 8 to ic acid. So phosphate. phosphoric acid. This is another case where the element keeps most of its element name, just like in sulfur, sulfuric acid. So sulfuric acid and not sulfic acid. Here we have phosphoric acid and not phosphic acid, right? You just gotta remember that, right? Okay, let's look at this one, H3PO3. PO3 is another polyatomic. We'll look it up here. PO3, 3 minus, the name of that is phosphite. Okay, so phosphite, will turn into us, phosphorus acid. Okay, you see that? I turns into us acid. And so that's all there is to it, right? So figure out what it ends in and then change the ending there. Okay. One more thing you're gonna notice, right? Remember we said oxo acid, it leads with H and it contains oxygen. So that's how you're gonna see how that's different than say HCl or HBr, the binary ones, right? But also something that else you should notice is you can have multiple protons in front, right? It leads with H, but you can have multiple. And how many H in front is dependent on the charge of the polyatomic. So nitrate being 1 minus will only need 1 proton to balance it out, right? It still needs to be electrically neutral, right? All compounds. So if your nitrate is 1 minus, you're only going to have 1 proton. So your chemical formula for the acid is just HNO3. But why is it H2SO4? Because SO4 is 2 minus. And so you need to balance out the 2 minus with 2 protons, right? And so that's why it's H2SO4. Well, guess why it's H3PO4? Because PO4 is 3 minus, right? So in writing the acid formula, you should know the charge and then just add however many protons in front. Okay. Let's do a couple more examples. But really, that is all there is to it. Let's do HBRO. So BRO is a polyatomic. Scroll down here and you'll see hypobromite is BRO negative. Okay, so hypobromite is the polyatomic that this is derived from. So I needs to change to us acid. Okay, so HBRO is hypobromous acid. Right? We saw that earlier. All right, I turns into this. Okay. One more. HClO4. Okay, so we'll look up ClO4. ClO4, up, we see that it is negative and it's called perchlorate. Perchlorate. So that 8 is going to turn into ic acid. So HClO4 is perchloric acid. Okay. So that's it. That's the 4 naming rules for the 4 different classifications of compounds. You got ionic, covalent, binary acid, and oxo acid naming. Okay. In this last exercise, I'm just going to throw some chemical formulas on the board without any classification. So you need to classify it first. Use the right rule in order to name it, right? So that's how you know that you've mastered this, right? Is when you're able to, just with any compound, come up with the name. Okay? So let's do ALF3. Okay. First of all, identify which one of the quadrant does that belong? Oh, it's a metal, and F is a non-metal. we got an ionic. So we need to follow the ionic naming rule. Aluminum, right? So Al just gets the element name. Aluminum is a metal. Figure out whether it's a fixed charge or variable. It's fixed, so you don't need parentheses. You don't need Roman numeral. And then look at the non-metal. It's F. Just a monatomic, so it's aluminum fluoride. That's it. Okay, let's go to B, PF3. PF3. Which quadrant does it belong? Non-metal, non-metal. So we're covalent. Okay, so it's going to be phosphorus. Remember how covalent goes? Use the prefix, but you don't need it for the first. You need mono for the first element. So it's just going to be phosphorus. 3 is going to be tri. And then it's root plus IDE for the second element, right? Fluoride. And there are 3 of them, so trifluoride. Phosphorus, trifluoride. Okay, C is H2SO3. What kind of, which quadrant is that, right? What kind of compound? Oh, it leads with H, so it's got to be an acid. But which acid? Oh, well, it has an oxygen in it, so it's oxoacid. Okay, so now that means I need to figure out what polyatomic it comes from. I see SO3. That is sulfite, okay? So I turns into us, right? Sulfurous acid. That's it, right? Remember, sulfur will get its full name, and then I turns into this acid. D, CaCO3. Which quadrant does this belong to? Well, Ca is a metal. CO3 is a collection of non-metal. So it's calcium, right? And then figure it out. Does it need Roman numeral? Calcium is in which group? Group 2A. So we don't need the Roman numeral. And the collection of non-metal is a polyatomic called carbonate. Okay, it's on the list. So the whole thing is just called calcium carbonate. Straightforward, right? One more. NH4F. NH4, you should recognize this one, your polyatomic. That's called ammonium. Okay, so all polyatomics, we just get it to a polyatomic name. So if you see NH4, it's ammonium. And how do you know that this is ionic? Well, NH4 is plus and fluoride is minus, okay? So here's a case where we have an ionic compound that's not metal and non-metal, right? But ionic compounds are broadly classified as plus and minus coming together, right? Does not necessarily have to be metal, non-metal. It just typically is, okay? And here's an example where it's not, okay? So, but don't let that confuse you, right? You still see a plus and you still see a minus. So ionic naming rule still applies. You're gonna name ammonium and then fluoride, right? Your monatomic gets IDE ending. Okay. All right, so let's try examples the other way around, where I give you the long name and then you give the formula. Okay, ammonium nitrate. How's that going to translate? Well, I should know, you should know, that ammonium is NH4 plus, right? I start to translate these into formulas before I put it together. Nitrate's a polyatomic, and I should know, and you should know, that is nitrate, NO3 minus, right? So now I can put it together. Remember, they need to be electrically neutral. One is plus, the other one's minus, so 1 and 1, 1 of each, right? So you just put NH4NO3. Next one, sodium hydrogen sulfate. Okay, so you need to see this as ionic as well, because you have a metal, right? And here's the collection of non-metal, which is your polyatomic. So just translate it, right? Sodium is going to be plus here, right? Because sodium is in group 1A. Even though it doesn't tell you that it's 1 plus, you should know that because sodium's in group 1A. We already discussed, right? Now, hydrogen sulfate is a polyatomic. We can look that up. Look at where hydrogen sulfate is. Hydrogen sulfate is basically a sulfate with one H in front of it, right? It's literal hydrogen sulfate. So if you know sulfate already, hydrogen sulfate is just, if you know sulfate as SO4 2 minus, then hydrogen sulfate is just put another proton in front, HSO4 minus, okay? So HSO4 minus, okay? So notice every time I'm gonna translate the long words into my symbols already, so that I'm ready to boom, put it together to make it neutral once I know the charge. So if this is 1 plus and this is 1 minus, it's just one of each. So I just put the sodium HSO4, NaHSO4, and that's my sodium hydrogen sulfate, right? Make it neutral. Okay. Let's keep going. Nickel 2. Fluorine, let's say. Okay. So nickel, the 2 tells you that the nickel is 2 plus. Remember, that's what the Roman numeral does, right? Now, chlorate, let's go and look. Chlorate is ClO3 minus. Okay. So how am I going to put this together so that it's neutral? Well, the chlorate, it's only 1 minus, nickel is 2 plus. So you're going to need 2 of the chlorates. So you're going to go NiClO3 subscript 2, right? NiClO3 subscript 2, because you need 2 chlorates in order to balance out the nickel, which is 2 plus, okay? So don't forget your parentheses. Okay, the next one, hydrofluoric acid. Okay, again, you need to figure out where does this go, which quadrant does this go, right? Hydro, there's only one type of naming that uses the prefix hydro. It's for binary acid, okay? So it's gonna be H, right? Fluor is F, okay? And you need to know that F is negative, right? Fluoric, that's negative. So just put 1 proton in front. Okay. Okay, as opposed to say E, hydrosulfuric acid. Again, hydro, it has to be binary. So it's only 2 types of atom. One of the atom is S. And so if you look at where S is in group 6A. So S will have a 2 negative charge. So how many protons are you gonna need? 2 to balance it out, okay? So hydrofluoric acid is HF, but hydrosulfuric acid is H2S, okay? Again, remember, the H is actually an H plus, right? And so it's counterbalancing the anion, right? So figure out what the anion is, and you'll know how many protons you need to put in front, okay? All right, one more. Aluminum carbonate. Okay, so first, figure out what quadrant you're in. Aluminum, oh, that's a metal. Carbonate, that's a polyatomic, non-metal. Metal, non-metal, it's ionic. Okay, if it's ionic, then I gotta make sure I know the charges, right? This is gonna be Al, and we need to know Al is 3 plus. It's in group 3A as well. So that's easy to see that aluminum is 3 plus, right? It's in group 3A. Carbonate, it's on your polyatomic chart. as CO3 2 minus. Okay. So now I need to put these together to make it neutral. One is 3 plus, the other one's 2 minus. Now, how many do I need of each? We're going to go with lowest common denominator, right? Which is 6. So 6 divided by 3 is 2. And 6 divided by 2 is 3. So notice I put parentheses around the carbonate and write the subscript 3. Okay. So that's what aluminum carbonate is. Al2, CO3 in parentheses, 3. All right, guys, we'll stop there. That's really the lesson on nomenclature. And I'll see you guys next time.